Characteristics define a wave's behavior. The highest point on the wave is called the crest. The lowest are the troughs. The amplitude is the distance from the baseline to a crest or a trough. The length of the wave is noted by the Greek letter lambda and is the distance between corresponding points on consecutive waves, crest to crest or trough to trough. Now let's talk about points that are said to be in phase. In phase points have the same displacement from equilibrium and are headed in the same direction. Let's take a look at this graph. What points on the diagram are in phase? D, F, and H, and C and E. Nice job. They are in phase because F, D, and H are traveling in the same direction and are at the same start position. C and E are in phase in a trough traveling up the wave. Why are B and D out of phase? Because they are traveling in opposite directions. Nice. Alright, let's keep talking waves. The frequency of a wave describes the number of waves that pass a given point in a time of 1 second. Frequency is measured in number of waves per second or hertz. For example, if 60 waves pass a given point in a second, the frequency would be 60 hertz. Because we use the equation number of waves divided by time. Related to frequency is the period of a wave, which is how long it takes a single wave to pass a given point. It is a reciprocal of frequency and is measured in seconds. Let's do an example. What is the period of a 50 hertz wave? Because period is 1 divided by the frequency, the answer would be 0.02 seconds. Nice job. Let's talk velocity. Because waves move through space, they must have a velocity. Based on our reference tables, we know all electromagnetic waves traveling through a vacuum travel at approximately 3 times 10 to the 8th meters per second. The speed of a wave is related to frequency and wavelength. Let's take a look at a graph of this relationship. As you can see, frequency and wavelength have an indirect relationship, and as frequency decreases, wavelength increases. This can be shown mathematically with the equation velocity equals frequency times wavelength. Take a look at a sample question. In a vacuum, all electromagnetic waves have the same. The answer is speed because all waves traveling in a vacuum travel at a speed of 3 times 10 to the 8th meters per second. Let's try one more. This diagram represents a periodic wave traveling through a uniform medium. The frequency is 2 hertz. What is the speed? From the diagram of the wave, we can conclude that the wavelength is 4 meters. Therefore, we use the equation velocity equals frequency times wavelength. Plug in 2 hertz for frequency and 4 meters for wavelength, getting our answer of 8 meters per second as the speed of the wave. Okay, now we are going to do a little experiment to verify the relationship between wavelength and frequency of electromagnetic spectrum. For this experiment, you will need a roll of paper tape, 3 colored pencils, red, purple, and green, a manila envelope with a square cut, a rectangle cut into it, and a ruler. What you need to do is take your roll of paper and make a start line as shown. Then, with your 3 pencils, you need to draw 3 lines all the way across, and at each line, take your ruler and measure out equal distances in the lines and mark them. As you can see on mine, I have markings. The red is 14 centimeters apart, the purple is 8, and the green is 10. This will help you with your experiment as we measure the velocity of the different colors. It's helpful to use textbooks to prop up the manila folder, and you need to insert your tape with the start in the opening of the folder. On the count of go, a person will pull the tape along and the recorder will count the number of times they see the lines for each color. At the end of the experiment, you need to take your results, and this will show you the velocity of each different color wave. The experiment will help you understand the relationship between wavelength and frequency of Roy G. Biv. Thank you for watching. I hope this helped with your understanding of waves.